Throughout the centuries, ancient Indian civilization developed significant scientific and technological achievements that were far ahead of their time. While modern historical analysis continues to evaluate these contributions, this video examines the documented evidence of scientific progress in ancient India between approximately 3000 BCE and 1000 CE, comparing these developments with later scientific breakthroughs. The ancient Sanskrit texts, particularly the Vaimanika Shastra, contain descriptions of flying machines called vimanas. While these texts date primarily from the early 1st millennium CE, they reflect concepts that modern aviation would only develop thousands of years later. These writings describe various aerial vehicles with capabilities such as vertical takeoff, different flying speeds, and long-distance travel. While no physical evidence of functioning aircraft from this period exists, the theoretical frameworks discussed in these texts demonstrate sophisticated conceptual thinking about flight mechanics and propulsion. Modern analysis of these texts reveals that ancient Indian scholars had developed theories about aerodynamics and propulsion, though without the materials science or energy sources to fully realize these concepts. These texts represent early theoretical work in aviation, similar to Leonardo da Vinci's flying machine designs that predated practical aviation by centuries. The Vaisheshika school of philosophy, founded by Kanada around the 6th century BCE, proposed that all matter consists of indivisible particles called anu. This atomic theory predated Greek atomism by at least a century. Kanada's work went beyond simple atomic concepts. His theories described how these fundamental particles combined in specific patterns to form larger substances, remarkably similar to modern molecular theory. The Vaisheshika Sutras outline classifications of these particles based on their properties and behaviors, establishing one of history's first systematic approaches to understanding matter at its most fundamental level. This early atomic theory, while lacking modern experimental validation methods, correctly identified the particulate nature of matter approximately 2,400 years before John Dalton's modern atomic theory was developed in the early 19th century. The Sushruta Samhita, composed around 600 BCE, documents surgical procedures with remarkable precision. Sushruta described over 300 surgical procedures and 120 surgical instruments, including specialized tools for procedures that wouldn't be replicated in Western medicine until much later. Most notable among these techniques was rhinoplasty, or nose reconstruction surgery, which involved grafting skin from the cheek or forehead to rebuild damaged nasal structures. This procedure was so effective that it formed the basis for plastic surgery techniques developed in Europe in the 18th century, more than 2,000 years after Sushruta first documented the approach. The text also outlines antiseptic practices, using specific medicinal herbs with antibacterial properties to sterilize wounds. Modern pharmacological analysis has confirmed that many of these plants contain natural compounds with antimicrobial effects, validating these ancient medical practices. Ancient India made fundamental contributions to mathematics, including the development of the decimal system, the concept of zero as both a placeholder and a number, and early work in algebra and trigonometry. The Surya Siddhanta contains sophisticated astronomical calculations. This text accurately calculated the Earth's diameter at approximately 7,840 miles and determined the Earth-Moon distance with precision that wasn't matched in Europe until the 17th century. Aryabhata's work in the 5th century CE included calculations of pi to 4 decimal places and the development of sign tables, essential for astronomical calculations. His mathematical work predated similar European developments by nearly a millennium. These mathematical achievements enabled accurate calendrical systems and astronomical predictions that were essential for agricultural planning and navigation. The Iron Pillar of Delhi, forged in the 4th century CE, demonstrates extraordinary metallurgical knowledge. Standing over 23 feet tall and weighing more than 6 tons, this pillar has resisted corrosion for more than 1,600 years due to its unique composition. Scientific analysis reveals that the pillar contains phosphorus and other elements in precise quantities that create a protective barrier preventing rust, a technique known as passive protection. This level of metallurgical sophistication represents knowledge of chemistry and materials science that wasn't replicated in Europe until the Industrial Revolution. Archaeological evidence from sites across the Indian subcontinent reveals sophisticated metalworking techniques, including the ability to forge weapons and tools with specific material properties suited to their applications. Archaeological findings at various Indian sites have uncovered artifacts consisting of copper plates and iron rods, housed in earthen containers. These structures bear striking similarities to basic galvanic cells or primitive batteries. Chemical analysis suggests these devices could have produced small electrical currents when filled with acidic fruit juices. While the exact purpose of these devices remains debated among historians, some ancient texts describe applications resembling electroplating and small electrical lighting effects. If these interpretations are correct, these would represent understanding of basic electrical principles more than a millennium before Alessandro Volta's invention of the modern battery in 1800. The scientific achievements of ancient India must be understood within their historical context. Many developments occurred gradually over centuries through the work of numerous scholars and practitioners. Knowledge was primarily transmitted through guru-shishya traditions and preserved in manuscripts that were vulnerable to destruction through natural disasters, conflicts, and the passage of time. The decline of major educational centers like Takshashila and Nalanda, due to invasions between the 5th and 12th centuries, CE disrupted knowledge transmission systems. This disruption, combined with the compartmentalization of knowledge within specific schools and traditions, resulted in the fragmentation of scientific understanding. European colonization further complicated historical assessment, as Western scientific paradigms often discounted or misinterpreted indigenous knowledge systems. Modern archaeological and textual research continues to provide more accurate evaluations of ancient India's scientific accomplishments. The scientific achievements of ancient India demonstrate that advanced thinking and technological innovation have emerged in multiple civilizations throughout human history. Rather than representing isolated anomalies, these developments show how human ingenuity has consistently pushed the boundaries of knowledge across cultures and time periods. Understanding these historical scientific contributions provides valuable context for the global history of science and challenges Eurocentric narratives about scientific development. It also demonstrates how knowledge can develop, be lost, and then rediscovered, highlighting both the resilience and fragility of human intellectual progress. Today's researchers continue to study ancient Indian scientific texts, not only for their historical significance, but also because they sometimes contain insights that remain relevant to modern scientific challenges, particularly in fields like sustainable materials, traditional medicine, and mathematical theory. By acknowledging and accurately assessing the scientific achievements of ancient India, we gain a more complete understanding of humanity's collective intellectual journey and the diverse paths through which scientific knowledge has developed across civilizations and millennia.